Okay, let's talk about the rate expression. So we're getting into the mathematics of kinetics. And so let's just look in a generic sense for a few minutes so that you'll understand the idea behind the rate expression. Then we'll get into the specifics of it. So let's say that we had a reaction where A is converted into B. Simple reaction, single reactant, single product. So A converts into B. And we're able to do some experiment, and we are able to determine the rate of this reaction. Say we graphed it out, and we were able to determine the rate. And the rate of the reaction was equal to some value. And that value is going to be related to the concentration of A, right? And so, and we changed the parameters of the reaction. We changed the concentration of A. Let's say that we took the concentration of A and we doubled it. And if we took the concentration of A and we doubled it, and the rate doubled, then we know that there's some relationship between the concentration of A and the rate. And so the rate has some relationship, some proportionality to the concentration of A. And that is a real simplistic way to look at a rate expression. How does change in the concentration of A affect the rate is what we're going to be looking at here. Okay, so let's look at rate expression. And so first let's just get a little generic chemical equation. So let's say that 2A plus B plus 3C makes some product over here, D. Doesn't really matter what it is. Let's write a rate expression for this particular reaction. And so rate is equal to K times the concentration of A raised to the X times B, or times the concentration of B raised to the Y, and the concentration of C raised to the Z. So let's define a couple of things first of all. And so K is the rate constant. K is the rate constant. Now, in chemistry, sometimes we have constants that aren't really constants. Temperature can change the rate constant. So the rate constant is constant as long as the temperature is constant. If the temperature changes, the rate constant will change with it, because you know that temperature affects the rate of a reaction. Okay. Now, the concentration of A, the concentration of B, concentration of C, you understand that. Raised to the powers X, Y, and Z. Now, an important thing to know here, really, really important, listen to this, is that these powers here do not come from the chemical equation. It's not 2, 1, 3. We don't put a 2, 1, 3 here. These powers are determined experimentally. You must determine those values via experiments, determined by experiments, the value of X, Y, and Z. And so this is a rate expression. This would be a rate expression potentially for this experiment here. Now, again, K is the rate constant, and the rate constant is only affected by temperature. It's not affected by the concentration of A or B or C or pressure or anything else. It's affected by temperature and temperature only. These values, X, Y's, and Z's, are the order of reaction. So X is equal to the order of reaction with respect to A, reactant A. Y would be the order of reaction with respect to B. Z would be the order of reaction with respect to C. Now, the overall order of the reaction, the overall order, now these are going to be numbers is what they're going to be. The overall order of this reaction will be X plus Y plus Z. That would be the overall order of the reaction. And so we're just kind of getting some definitions, some terminology out of the way right now. And so this is a rate expression. You could call it a rate law. Would be another term that you might be able to use here. So a rate expression, K is the rate constant. The brackets, again, you know that means concentration. The concentration of A raised to the x, concentration of b raised to the y, concentration of c raised to the z. X, y, and z are determined from experiments. They are not coefficients from the reaction, okay? And the x, y, and z are the order of reaction with respect to that particular reactant, okay? And the overall order is add up the individual orders of reactions. Okay, let's move on. So here's another generic equation. A plus B makes C. Here's the rate that this is the rate expression we've determined the experience. Now we have numbers in here, a 2 here and a 1 here, so this has been determined. Okay, and so let's kind of decipher this a little bit according to what we just talked about. And so what is the order of reaction with respect to A? The order of reaction with respect to A is 2. The order of reaction with respect to B is 1. Okay. Now, what does that mean? Let's just take this and break it down to what does it mean. Well, what that means is that, for example, B, if we took B and we doubled B, doubled the concentration of B, then what that's going to do, so let's say that the concentration of B is 2. Okay, so there's a little 2 in here where B is, and we multiply all this out here and we get the rate. Okay, well, let's say if we took B and we doubled it, we made it 4. What happens to the end answer over here to the rate? Well, if you doubled the value of B, then whatever these numbers equal up to, we're going to multiply it in and we're going to double those values, and so the rate doubles. And so if a reactant is a first order reactant, what that means is that whatever you do to that reactant, you do the exact same thing to the rate. So if you double the reactant, you double the rate. If you quadruple the reactant concentration, you quadruple the rate. If you half the reactant concentration, you half the rate. And that's what it means to be a first order reactant. So B would be a first order reactant. Now, A is not first order. A is a second order reactant because there's a little 2 here. Now, again, just kind of looking at it, if I took A, let's say that the concentration of A was 2, and I doubled 2, so in here, if I have A is equal to 2, and this would be 2 squared, so 2 squared is 4, okay? If I doubled A, and so A became 4, and 4 squared would be 16. If I double the concentration of A, I don't double the rate, I quadruple the rate. I square the change, and so I quadruple the rate. That's a second order reaction. And so what the rate expression does is it tells you how by affecting the concentration of my reactants, how am I going to change the overall rate of the reaction? How does changing the concentration of different reactants affect the rate of the reaction? That's what a rate expression does for you. Okay. Now, the other thing is, what is the overall order of this reaction? Well, the overall order is equal to 2 plus 1, or 3. It's a third order reaction. It's second order with respect to A, it's first order with respect to B, and it's third order overall. And that is what this kind of reaction is. It's a third order reaction. Okay, and so this is your basic information on, it's your foundation on rate expressions or rate laws. So how does affecting a reaction, how does affecting the concentration affect the rate? What if this, instead of having A plus B makes C, what if it was A plus B plus C equals D, and we had the same rate expression where there was no expression of C in here? Okay. Well, if there's no expression of C in there, what that means is it's a zero order with respect to C, which means changing C doesn't change the rate. The concentration of C has no bearing on the rate of the reaction at all. It has no effect at all on the rate. It's not important what the concentration of C is to the rate of the reaction. And so that is what a zero order would be. And so if it's a zero order, we don't need to write it in the reaction.